So indeed, today I'm going to talk about AtomVM and a specific project called La Machine. La Machine is a useless box, and that's just powered by Erlang and using AtomVM. So first, I'm going to show you a quick video of La Machine prototype, which is what you can see here on the screen. So La Machine is actually this prototype you can see here. So it's a useless box, which means that it's a kind of device where when you press the button, there's a finger that goes out with some sound, which is specific of La Machine, and that just closes it. So this is the very prototype you have here that just came here from Paris in train. So this is today's agenda. So I'm going to unplug this because, well, anyway. That's the script that was used for the video, so I don't want to be interrupted. Anyway, so today's agenda is a brief history of La Machine, just to tell you how it came to life. I'm going to talk about hardware, because this is a talk about hardware and IoT. I'm going to, of course, to explain about AtomVM. Well, this is kind of trick, because this is code Beam, and AtomVM is a competitor of Beam. But yet. And I'm going to talk more specifically about what it means to do software engineering for microcontrollers, especially with Erlang. And then I go even further, because just like some people might have tried AtomVM in the audience, if you want to go even further, so how you can extend AtomVM with native code, what we call NIF in the Beam ecosystem. So brief history of La Machine. So La Machine is a device, as I showed you, but eventually first, the idea was invented by this guy, Marvin Minsky. He invented what he called it the ultimate machine when he was an intern at Bell Labs. So next time you wonder what great invention came out of Bell Labs, you can mention the useless box or the ultimate machine, not Unix system, okay? So he created this with Cloud Channel and so on, and eventually it got built pretty quickly after its invention in 1952. So you can see a video of him explaining how he came about this idea. Then fast forward to 2005, there is a guy called Olivier Mével, and actually he's a friend of mine now, and he wanted to build a useless box, just drawing from Marvin Minsky. But eventually he decided to create a Wi-Fi rabbit, which I think is the closest you can imagine to a useless box, because the Wi-Fi rabbit just doesn't do anything. I mean, it can tell jokes on a regular basis. It just shows colors depending on the weather, but I mean, you could look through the window. It can give you the time, but anyway, so he created this Wi-Fi rabbit with Raphaël Adjan in 2005. So in 2007, actually, I joined the company behind the Wi-Fi rabbit, called Violet, as a CTO, and this is when I work on many projects, including improving the way these Wi-Fi rabbits, because even if they were useless, they sold like thousands of them. So how to connect these Wi-Fi rabbits to the internet and together. And this is how I decided to implement, to change the network architecture of the rabbits, from what it existed, which was HTTP, to XMPP using eJabberD, and with the help of Process One. And actually, Process One, they just boast about this on their website. I was very proud when I saw this. And so this is how I came to come to try and admire Erlang. So I've been an Erlanger since 2007 only, based on this. So it was very nice. It worked very well. I mean, the communication. Well, commercially, not that well. Eventually, Nabastag, the company, Violet, actually went bankrupt. So quite a different story, because it went bankrupt not once, but twice. I mean, it went bankrupt first, and then another company decided to purchase it because they were in love with the rabbit that was useless, and this other company actually went bankrupt, and it was bought after that by a third company called Aldebaran Robotics, who just build robots. You might have heard of them. They did not went bankrupt. I mean, they got a huge amount of money from SoftBank Robotics, but eventually they decided to cancel the servers, and so the Naba stack became useless. I mean, more than before, because they could not connect to any server. And this is the moment when I met again with Olivier. And in 2019, he said, oh, we should try a new kind of rabbit where it's not going to connect to server, but it's going to be entirely local. And he was like, oh, we could put a Raspberry Pi 0 into the rabbit. And so that was a very exciting project I worked with him on, including the part where I did implement speech recognition in Raspberry Pi 0, which didn't work very well, but that was fine because in 2005 it didn't work well. So, so it works as bad. And also, the problem was that I tried to convince Olivier to build this into Erlang, but he said, no, we should do Python because a lot of people are going to produce open source code and so on and contribute if it's Python more than Erlang. I said, okay. So most of it was written in Python, but I was able to sneak in some Erlang, especially when I used these rabbits to teach programming to kids. So at that moment, my children were in school, were quite young. And so I built a school Erlang app where you can program the rabbit using Erlang. So Erlang is technically running on this rabbit, on the Raspberry Pi 0. But this is just regular beam. I mean, Raspberry Pi 0 is a very powerful microcontroller. I told you, it can do speech recognition. So, and run Linux. Two things from Bell Labs. No, on Linux, actually. So this is how I was able to sneak in some Erlang into one of Olivier's projects. And in 2024, I mean this year, as I was switching jobs, Olivier said, okay, that's a perfect moment to launch La Machine. So he prototyped this, and this time I convinced him to do it in Erlang. So I said, okay, that's okay, we won't do it in Python, we're going to do it in Erlang. And so eventually, La Machine and this prototype, as well, this is what you see in the video, is running Erlang using AtomVM. So what is La Machine hardware-wise? So La Machine hardware-wise is like this. There is actually, I brought a broken down prototype because I shouldn't damage this prototype because it was so expensive, Olivier told me, so I need a steel frame, right? So this is what the prototype is about. So you have a small board like this. This is the picture you can see is very similar to the one that you see on the screen. You have a button, a switch button. You have a servo for the arm. Here it is, like a motor. You have a speaker, an amplifier. You've got some external flash, a battery, and the charging logic. And the microcontroller itself is an ESP32C3, so it's 5 millimeter by 5 millimeter, very small. So the ESP32C3 is a 32-bit processor running single core, running at 160 megahertz. It only has 400 kilobytes of RAM. Yeah, kilograms would be quite heavy. 400 kilobytes, 400 kilobytes of RAM. And it's ultra low power, so it means that when it's sleeping, in deep sleep, it only uses 5 micro amps, and so it means that you can have very long battery life when it's sleeping, which is what La Machine is doing. I mean, most of the time, it doesn't do anything, so it sleeps. So the question is, how do you run Erlang on such a small processor? And so this is the moment I introduce you with AtomVM. So AtomVM is the ability to run Beam apps within 400 kilobytes or less. So AtomVM, what is AtomVM? AtomVM is a virtual machine for IoT devices. The project was created by David Betio, and actually I came upon this when I was working with Olivier on another project, which unfortunately I wrote in C, so I'm not talking about this here, probably in Code C conference in a few months. So, so in this case, I found this project was so exciting that you could run Erlang into very small microcontrollers. And initially, it was mostly targeting ESP32. And now, it works on every ESP32s. So I have many. I can show in a workshop, well, some meetup later today. It also works on STM32, which is another family of microcontrollers. It works on Raspberry Pi Pico and Pico 2, which are also very small controllers. And it even works, because it's so small, in the browser using WebAssembly. So you can technically run Erlang or Elixir in the browser. So the way it works is you have a subset of Erlang OTP standard libraries, a subset of Elixir libraries. We've been discussing about how to run this in Gleam. Someone tried this. This is something I discussed with Louis earlier today. And Lua could be quite fun. And because Gleam is so sexy with the Gleam run page that you've probably seen, where you can type Gleam and just translate to JavaScript and execute immediately, I know that Jose was a bit probably envious that you couldn't do the same thing with Elixir. And so eventually, in a few hours, I mean, a weekend like 2 weeks ago, I built this language store when you can edit code directly in browser in Elixir running, and then it's going to edit it. So I put a video, right? So I type Jose, and it works like this. So this is just AtomVM, not only running on microcontrollers, but also directly running in Safari in this case. If we go to what are the APIs that are available in AtomVM, there is something very common into microcontrollers called GPIOs, or general purpose input-outputs. So the ESP32C3 has 22 of them. So we use them for everything. So for example, we use them for the button. So you read the state of the button. So if it's 1, the button is in one position. If it's 0, it's in another position. We also use it to enable the servo. So the way it works, because we want to limit the amount of electricity or power they use in the machine, we try to shut down everything we could. So the servo is running at a given voltage, 5 volts, and we want it to run always at 5 volts, because otherwise the speed is going to be different depending on the state of the battery. You know, I mean, all the kind of engineering you have here. And so there is some kind of boost that just takes the voltage of the battery and puts it up to 5 volts, and we just enable or disable it with a GPIO. So we use GPIO for this. It's also used through audio. I'm going to talk about this later in this talk. But also, likewise, to enable or disable audio. So there is another pin that you can see set to high or low, and just to disable audio. And so it uses less memory, less power, also detecting the charge. And pins, as you can see in this diagram, in the case of the machine, are also used for the flash, so external flash, and to read the battery voltage. Very common. Of course, AtomVM can do all of this. Another thing that we're using is the servo itself. We can drive it through what is called pulse width modulation. So pulse width modulation is a way built into microcontrollers where you can have, in a given period, in this case 20 milliseconds, to have a pulse of a given width. And typically it's used in LEDs for pulsing, right? And if you had a MacBook back in the days when they only had this, or the iBooks, you know, they were known for pulsing when they were sleeping. And so they were using this technology. But it's also used for controlling servo motors, like the one in the machine. So because it's used so much with LEDs, the module in AtomVM to do this is called LED-C, in both Erlang and Elixir. And if you want to do the same in Pico, that's possible, but the module hasn't been ported yet, but just raise an issue in the GitHub repo, and we could do it very quickly. And the other thing which is very fundamental of La Machine, and the reason we're doing with ESP32, is deep sleep. So deep sleep, what is it? Deep sleep is a way for a microcontroller to stop and to be woken up by some external causes. So in this case, we want it to be woken up by a GPIO, so for example, the button. So we want the system to stop, and if the button is pressed, it's going to wake up. Or after a delay. I'm going to talk about this later. This is 2 mechanisms we're using in La Machine. So the API is pretty straightforward. So we just say ESP, deep sleep enable GPIO wake up, and then you say which GPIO you want to enable, and whether you want it 1 it is high or 0 when it's low. And after a delay, just call deep sleep and provide number of milliseconds you want to sleep. Also, because we have several causes that can wake the system up, there is another function called sleep get wake up cause, which you can call to figure out whether you've been woken up because of the delay or because of the button. And the other thing which is important in this sleep is very few kilobytes of RAM persist, because to be able to use as less power as possible, you don't have all the 400 kilobytes of RAM for this. Only have 8, which is quite large. but you cannot run Erlang on it. But anyway, so the way we do it is you can save the amount of you can save all this into with set binary, and you can get it with get binary. The reason it's called RTC slow set binary and RTC slow get binary, it's the name of the API in ESP, is because this RAM is slower than regular RAM, hence slow. And RTC is because the same electronic circuit that powers the clock, and you're going to see it's important. So in deep sleep, the clock is still running, the processor stopped. So when it resumes, when it wakes up, it just starts from the beginning. So you go at the beginning of the start function, but still the clock is still running. And so you can use this memory around this. And based on this, the biggest success with the first version of La Machine, this prototype I showed you, is that eventually it only draws 18 microamps when sleeping, which the battery would mean probably more than a year. And the goal was just a few months, so we're good. Of course, when you use it, it draws the battery. So I'm going to talk a bit more about the sleep logic, because this is a part that was quite complex and actually where most of the logic was tested with specific unit tests. So the specification was the following. First, very easy. If user presses the button, you wake up and you play sound, and then you go to sleep. But what Olivier wanted, and I think it's very interesting, is if user didn't press the button for a while, you need to poke them, which means that you need to do something, probably not a sound, but at least use the motor to open the box. But you don't want to do this when the user is sleeping. So the question is, when do you do this? And also the third aspect is, if the battery is going to be depleted, you want to make sure that the machine is in such a way that eventually the user figure out that it needs to recharge it, so not closed. So the way it works is the clock origin is random. Why? Because La Machine does not connect to the internet at all. So there is no notion of what time it is or whatever. But we know when the machine was first powered, I mean, from a hard reset, the first time you powered it. So we have some kind of origin of 0. And so the way it works is every time the user presses the button, I just look at the hour. So I just look at the time based on this origin and then divide it on only 1 hour from 0 to 23. And I store this into a huge array of hours. And so to figure out when is the best moment to poke the user, I just choose one random hour from this array. So if the user plays with the machine at 3 a.m. in the morning, it's going to do it again. But if he only did it once and usually use it at 3 p.m., it's going to be more likely to do it at 3 p.m. So the way it works. So I choose the hour based on the moment when the user actually pressed the button. Another thing that's important in La Machine I wanted to talk about today is, in OTP you have some mechanism to make sure that eventually when there's a crash, it restarts and so on, which is very nice. And you want to use this kind of mechanism in IoT as well. In the case of La Machine, the life cycle between 2 boots is very small, because just plays and then we sleep, so it's kind of shut down. Nevertheless, there is a mechanism which is not OTP side, but quite useful. It's the watchdog. So the watchdog is what? It's very common for microcontrollers, is you just tell the system to restart if there is if you didn't flag and say, I'm still alive, and everything is okay. And the way I use it is just at the very beginning, I just set up a watchdog and say, okay, if I don't turn off this watchdog or I don't say everything is okay in 1 minute, you can crash and restart, and then we start from the beginning. And so we know we're not stuck. And eventually, because we want to make sure that the machine is deep sleeping to be waken up by the button. And so this is how it's programmed, and very quite useful. So here a few words. La Machine is running with ESP32, which is on the microcontrollers the AtomVM is working on, probably the most closest to a real operating system. There is a free RTOS running, and so we have got some kind of task in the background that can run. If you look at the Pico, there is no operating system at all. So we're going to talk about this later in this talk, but we do it differently. So now I'm going to stress into how you do debugging, testing, and typing, or what we could say software engineering for IoT. So embedded software development is a bit different from regular software development, because what you do is you write code, you download, and you test. Usually you write code and you test. But in the case of embedded software development, you need to reflash things every time. So something that's very cool with AtomVM is you only flash the Erlang code or exit code you're writing, and you don't need to flash the VM every time. So which means that it goes faster. You just flash few kilobytes usually because your code is not so huge. So this is how you do it with LWord. So I just encourage you to try. So you just have to install some tools to be able to flash, to download the AtomVM release image, for example, for the ESP32C3. Then you flash it with the tool. Then use Rebar3 plugin to upload your code, and then you test it, you update the code, and you go back to step 4. Okay. Debugging is to be able to get some information from the VM, and you can use some serial emulator. And on ESP32, it's better to use actually the specific tools, because then they connect to the device and they start the program at that moment. So which means that you have the serial output from the very beginning. This is where you can see the AtomVM banner, that virtual machine that you can see. Otherwise, if you connect with serial emulator, you get it later. And here you can see a crash that I actually had happening working on this presentation because I forgot to include the crypto libraries, because we don't have a lot of memory. You can configure in AtomVM what kind of libraries you want to include, and I forgot to include crypto libraries, and it didn't work because you're using it for random numbers. On Pico, there is something specific, which is we managed to figure out how to only start the program when you connect it to serial or after a delay. So if you forget to connect it, it's going to start eventually. You can run tests using eUnit, and you should run tests using eUnit or, well, any testing framework, but eUnit is what we support. What is good is this: how I did test the deep sleep mechanism, I mean the algorithm to figure out when to wake up. The test, you can run them both on Beam, so regular virtual machine, and AtomVM for Unix, because AtomVM can compile to Unix, so you can compare the behavior. And it's very suitable for everything which is not related to the API that's specific to ESP32. So this feature is going to come for next release of AtomVM, next major release, 0.7, but you can do it from the main branch. Also, you can do it with an emulator. So it's always faster to do it on emulator than with hardware. So the thing is, if you use the eUnit test with AtomVM, eventually it's compatible with Unity, and you can run the test using ESP IDF qemu, which is very nice, and then you can test all the problems you have and so on. And so we do use qemu for AtomVM to test everything, including SMP, including networking, including SD cards, which we do support. And for Pico, we use rp2040.js, which is an emulator for Pico. And the team is also working on WorkWe CI, which is a commercial solution that is more or less free for open source projects. And of course, you can dialyzer, which is cool as well. And this is very useful because with AtomVM, because you don't have exactly the same functions, when you run dialyzer, eventually you figure out what are the incompatibilities. I mean, maybe you used to use a given function that we didn't port. You can figure out before flashing to your device. You can do it faster. Unfortunately, it's not compatible with your bar3 dialyzer target, so you can do it the way I show it on screen. And all this actually is implemented with La Machine in the CI directly on GitHub Action. So. Then eventually I'm going to finish with adding some native code, which is the question that often comes up when you want to do some IoT development. And the example I'm using is sound. So for La Machine, I am using a framework called ESP ADF for AAC decoding or MP3 or all the stuff. Actually, the sounds are AAC because you get a better quality for the same size of the sounds. So the way it works is this was ported as a NIF with resources. So I don't know if you're quite aware about resources, a very cool addition to the Beam visual machine. It's been quite many releases now. And so we have the same thing in AtomVM. And so on AtomVM, you can use ports or NIFs. So ports was the initial way, I guess, to do some kind drivers in AtomVM. There are schedule-like processes, like Erlang processes. They are run when a message is received. They can send messages, and they can receive messages from listeners, which I'm going to cover next slide. While NIFs are synchronous. They are easier to port. They can rely on resources. Resources can be selected, so you can use select, which is very useful. We use it for sockets. We use for many other things. And you can monitor processes. Of course, you need to be aware, like with the Beam virtual machine, that the same disclaimer apply. I mean, a NIF should not be dirty. We don't have any dirty scheduler. So if you stop the execution for a while, well, nothing happens, and these kind of things. So listeners, and I'm going to cover this in more detail now. So listeners, the way it works is on microcontrollers, you can have some interruptions. And on interruptions, the way you do it is usually you enqueue an event. For example, let's say that you want to be interrupted when some signal comes from a GPIO. Let's say you have some accelerator, you want to figure out when there's a talk or the device falls or something like that. Then you should enqueue an event. And on ESP32, use XQ. You can also use FreeRTOS task, which can enqueue event or they can send a message. And eventually, this is picked up by the scheduler thread. So the scheduler thread works like this. It loops forever. It picks up a process ready to execute, has something to do. It runs code until reduction counter reaches 0 or the process is waiting for a message. And then it checks the queue that was enqueued by the interruption or by the FreeRTOS task until a given timer expires. For example, if you want if you do a receive after with the timer, this is the timer, and then it runs listeners on the queue event. So eventually, this mechanism is such that if there is nothing happening, even if you're not deep sleeping, the process is going to halt, which is good. But you need to pass messages from interrupts and from FreeRTOS task. And this means that this is a golden rule, which is very important, is you shall not send a message from interrupt handler. I'm going to explain why. When you send a message to another process, typically what you do is going to do some memory allocation in your interrupt handler. So memory allocation, normally you cannot do it in interrupt handlers because there can be some locks into the memory heap. On ESP32, you can do some memory allocation, but they say, oh, maybe we're going to deprecate this feature, so I wouldn't suggest doing it. And when you send a message, eventually you're going to lock the process table to figure out who to send the message to. And so the reason it's a problem is, let's say that you lock the heap or the process table, and then there's an interrupt, then your code is executed, and if your interrupt's right to lock the heap or the table, then it's a deadlock. Because your interrupt, nothing's going to be executed, and you've got two locks, and so that's the end of your IoT device. You need to restart it manually. It's possible to send a message from a given FreeRTOS task with a specific API we developed that do some magic like trying to lock, and if it cannot, unqueues the message and so on. The other thing is about memory. So each process has their own heap, which means that all the bytes are there, the objects are there, and so on. And so you call a function called memory ensure free to allocate memory on the heap. This can be garbage collected. You do it only in NIF and ports. And you also can create a specific heap for listeners to have more place to send messages. You shall not allocate terms on another process heap. I mean, you cannot grab a process and say, I'm going to allocate terms on this. It's going to be very bad, especially when you're running SMP. So SMP was a feature that eventually I did develop for AtomVM, because when I joined the project, they didn't have SMP, and I thought it was sorry, because one of the power of Erlang is to be able to run things in parallel. And at some point, I felt some regret, because SMP introduced so much burden and hassle and makes things so much difficult. Everything I just explained, most of them are because of SMP interrupts, so it's quite complex, but still, I mean, eventually it seems that the team is happy with it. So the way it works is you have one scheduler per core. So on the Pico that has 2 cores, you have 2 schedulers. The first ready scheduler is going to pull events from interrupts, and you need to have some synchronization happening. And so it works on all ESP32 that has several cores, so ESP32, 32S3, P4, the Pico and Pico 2. It works on generic Unix, and also on the browser, the demo I showed you, it runs many process schedulers in parallel, like 8, I think, depending on my laptop, because it's only a 16 cores, whatever. And so I just show you in this benchmark how much speed we get having a second core. So we're using the second core not exactly, so not 100%, which would mean that the SMP would be perfect, but it's quite close. So we've got the Pico, Pico 2, and Pico 2 is a very funny port because you can run both ARM and the RISC-V core. Okay. So then I'm going to finish with the next steps and the credits about this talk. First, few words about La Machine. So La Machine, we're going to work, well, we are working on the version 1.2 of the hardware with some fixes. Also, we're going to add an accelerometer just as I said. What the reason is following. Eventually, when this design was made, the charging was at the bottom. And so I thought, okay, that's nice to have the charging there. You know, like the mouse from Apple that you can only, you know, okay. So if Apple does it, maybe you can as well. So the reason is there is because it was too expensive to do it here for engineering reasons, so it's supposed to be here. And the problem is, if you charge this way, you don't want the machine to operate. And so we thought, how do we do this? So one way would be to try to detect if it's charging, but maybe you put the box like this and you unplug the other end, but you don't want the box to open because you don't need to reveal the magic. And also, the other reason is the cover, I mean, goes down just because of gravity. So eventually, we decided to introduce an accelerometer there to detect. Oh, yeah, Olivier's going to kill me. Oh, okay, no, that's fine. So. So we're going to add an accelerometer, and I need to take care of this. So this is about the hardware roadmap. Software roadmap, we're going to indeed implement the accelerometer and maybe the wake up, because obviously once you have an accelerometer, you can do a lot of funny things, like maybe like the, you know, you put it this way and there's some sound. Remind you maybe of something. Okay. And also another thing we want to do is sequence behaviors. Like when you pour it on, it may play a sound, the first sound, and then if you pour it on a second time, but close enough, it goes the second sound in the series, the sequence of the first sound. And there is another thing that we're launching is La Machine in Lego. So I'm going to show it this way. So I hope you can see. And so you can see in the picture, this is very same. And so likewise, of course, there are several sounds, and they're different. But it's random, so I got the same twice. Anyway, yeah, I mentioned it's crypto random, right? So pretty high quality random. So yeah, so the Lego, and I think Olivier just launched the pre-order for this, and he hopes to be able to deliver by Christmas, something like this. So let me try. I'm very unlucky. Okay. And also the lab machine is going to be launched as part of Kickstarter campaign and starting earlier next year. So just this talk wouldn't be possible with all the team around AtomVM. So a lot of people working on this. David DeBetio, of course, we just originally created the project. We had one core member called Fred, who unfortunately passed away last year. Or earlier this year, so it slowed us down a bit, and we are, of course, very sorry. So we've got the name of the contributors. La Machine, you can find it online, and Olivier is not alone, also working with someone for electronic and design studio, and the Lego is by Loïc Brun. And I should mention that I came only by train, so I just need to thank Deutsche Bahn for the way in. And maybe and SNC for the way out, so I wouldn't thank them. I only mention them. We'll see after when I return. Thank you. We're going to organize a small meetup session at 3:30 this afternoon. I just brought a lot of other devices running AtomVM, and if you have some microcontrollers, we can play with this as well. So thank you.
Right, thank you. We are right on time, so we have some time for questions as well. Raise your hand if you have a question.
Oh, yeah. Mention something about ALISP.
Oh, yeah. So, so indeed. So there is a Lisp interpreter in AtomVM developed by Davide, which is called ALISP. So you can run ALISP REPL directly on AtomVM. It's built in. So yeah, this is what I think you wanted to mention. LFE, we didn't try LFE, but ALISP, I mean, is quite a strong competitor for AtomVM. I mentioned that Gleam, we're still working on it, or some people are, and Lual could be quite interesting, but I'm not aware of anyone trying it.
Are there any plans to use the accelerometer to detect, like shaking it or throwing it or whatever, to make it do something like shut up at 3 a.m.?
Interesting suggestion, yes. The thing is, you don't know if it's 3 a.m. or maybe some kids playing with it, so we need to take into account, because as I said, usually ESP32s, they're very popular because they provide with Wi-Fi and Bluetooth and so on. But in the case of La Machine, we decided not to include anything like this, just for simplicity of electronic design, actually. I think Olivier plans to make a Wi-Fi version later. But you know, after the Wi-Fi rabbits, he realized that you can do useless things without internet. So, but the drawback is we don't have any access to the time. So we don't know what time it is. So maybe we could have some detection of the lights to figure out whether lights are on or not. I don't know. I'd love to put a lot of sensors into the objects.
First of all, thank you very much for looking into Gleam as well. Maybe take a look at the standard library. It's very small. If it passes unit tests and everything, that would be nice. And a question about AtomVM: how much in terms of bundling up as a CLI runner or bundling up in the browser? No, not bundling up as a browser. Sorry. How big is it if you want to ship it? Like ship AtomVM with an Erlang or Gleam or Elixir program. How big is it?
Yeah, excellent question. So AtomVM is very small. On La Machine, we have 16 megabytes of flash, but usually on the most ESP32 controllers, you only have 4. And AtomVM takes about 2 with the standard libraries, which means you have 2 megabytes for your program, so it's quite small. So you've got everything in 2 megabytes. In the browser as well, the virtual machine itself is quite small. The demo I showed you with running Elixir evaluation directly in the browser, it uses both AtomVM and also some Elixir direct core beams that are loaded, and it works. It's quite small as well. I have the same thing with Erlang, and in this case it's big because I needed the Unicode util module, which is 1 megabyte or something like that. So, but just because, well, I was missing some function and that the core library were using the Unicode util. So anyway, just few megabytes. So a couple of megabytes is sufficient.
Very briefly. Okay. The Elixir demo that you showed, how much kilobyte is that?
I think it's only maybe less than 3 megabytes. We can check out. Maybe less than 3 megabytes total loading into the browser. And mostly beam files.